But perhaps more importantly, the convexity is not the right notion of convexity for it to even make sense. So in fact, it just plainly doesn't work even for the scalar models.
I see.
So yeah, I changed the plan.
Yeah. I'm just getting the YouTube set up.
Thanks.
Okay, YouTube is on, and I'll start the recording.
All right. Thanks. So hi everyone, welcome back to this series of lectures on the statistical mechanics of disordered systems. So so I see that there's a question in the chat about the SK model. So I'll start by answering this question. So the question is about whether there is some sort of universality for the SK model if we try to replace the JIJs, these random couplings, by something which is not Gaussian, and the answer is yes. So if we can replace, so if we replace these by still independent random variables, which are centered and have the same variance, and let's say have a third moment, or maybe I think third moment is enough, then in the limit the behavior is the same. And in fact, it's easier to prove this for spin glasses than it is to prove it for statistical inference. And this is an idea I actually, for statistical inference in the introduction, I try to make a connection between the model we studied and this community detection problem. And in the community detection problem, there are no Gaussians. And so at some point I had to kind of make some analogy between the true model and the model with Gaussians. And I use this heuristic. If I make sure that the mean is correct and the variance is correct, then things are fine. Okay, so in general, everything is fine as long as we talk about random variables which are much more numerous than the number of sites. Okay, so the X bar in the statistical inference case, these we cannot do this sort of manipulation, but because there are much fewer of them. But as long as you can average, as long as there are enough variables per site, you can do this argument. It's kind of a local CLT, like a CLT for each individual unit in some heuristic sense. All right, so last time we started to build some tools that will allow us to. So you remember that our ultimate goal is to try to get our hands on the limit for energy of these spin glasses. And in order to do so, we need to find a suitable way to enrich the energy function so that later, when we compute derivatives of the free energy, we find relations between the derivatives with an error term that becomes small as n goes to infinity. And we had tried one first attempt, but that was not sufficient. And now we are kind of expanding our toolbox so that we're to be able to ultimately propose a better candidate for enriching this energy function. And last time we discussed Poisson-Dirichlet processes. So let me write this again. So this is encoded by one parameter zeta. And zeta is between 0 and 1. And it's constructed as follows. So we take UN, a Poisson point process with intensity measure zeta over x to the zeta plus 1 dx. So restricted to x positive. I don't write this each time. And here you remember that we can order this decreasingly. So I think that U1 is the largest point, and then U2, etc. And these points accumulate to 0. And then we set Vn to be Un divided by the total sum. Okay, so the result of this point process normalized so that the total sum becomes equal to 1 is the Poisson-Dirichlet process with parameter zeta. And perhaps it's useful to, so this is supposed to try to capture the weight of our Gibbs measure in the limit. And as a toy model that we can think about, we had discussed last time the situation in which we have 2 to the n independent Gaussians, and we look at exponential of beta square root of n times these Gaussians. And so in this case, I claim, and it's explained in more details in the problem set, that as n goes to infinity, indeed, the extreme points of this family of random variables look like this Poisson point process. And so if we normalize these things to be a probability measure, they will look like this Poisson-Dirichlet process. Is this in terms of the weights? And now it's perhaps useful to try to do a drawing of what happens in terms really of even the geometry of our space. So if we think that the configurations are indexed by, let's say, the points of the hypercube, the -1 to the n, then we can embed this measure into, this measure kind of lives in Rn. And asymptotically, we said that the weights of the measure should look like this Poisson-Dirichlet process. And because we're picking independent random variables, the directions that will carry these weights will be all orthogonal to one another. Okay, so maybe it's hard to do pictures in very high dimension, but at least I can start to draw some directions which are all orthogonal to one another. And it's anyway, you get the idea. Okay, so maybe they will all these configurations will all live on some sphere, and so this will be the configuration with weight v1, this one the weight v2, v3, etc. And you should imagine that it's in very high dimension, and I can continue to have many orthogonal directions like this, okay, which will all carry v1, v2, v3, etc. And perhaps, so this was perhaps the first toy model we can think about. And perhaps it's not unreasonable to expect that, at least in some context, for instance, if there is a bias in our +1 - 1 measure, then in fact, they will not be all orthogonal to one another, but they will all have some tendency to be in some direction. And then they will pick some independent directions. So maybe another picture that we could have in mind is that, So they would all form the same angle between one another. So I'm not sure exactly how to draw this, but you should imagine that this triangle is equilateral, and like all of these points have the same angle between one another, or in other words, these vectors have the same scalar product, and similarly we could have v1, v2, v3, etc. This would also be let's say a plausible scenario for what our GIST measure could look like. And yeah, perhaps it's okay. So I'm just going to reformulate the same picture as I said. So here I presented it as you pick vectors which are all having the same scalar product between one another. But one convenient way to construct it, so this is actually really the same picture, is to think of it as you're first picking a direction which is not quite yet reaching the boundary of the sphere. And this is kind of the commonality between all these vectors. And once you're there, you're picking orthogonal directions in the orthogonal hyperplane. And then you stop when you touch the cube. Okay, so then once we're there, we could like draw a circle like here and draw orthogonal directions. So you should imagine that they are all orthogonal to one another, and this would be v1, v2, v3. Okay, and so this is really the same picture. Okay, I'm just thinking about it in a different way. And so unfortunately, so I hope so far things are okay. And yeah, unfortunately, this is not yet quite enough to manage to capture the way the GIST measure is going to look like in our spin glass model. Because in reality, what will happen is that we cannot exclude, and in fact, it does happen that the GIST measure looks like a hierarchical composition of the picture I just said. So you should imagine that, in fact, maybe hidden in this point, let's say, there is in fact a substructure, and this substructure is described exactly in the same way I said. So everybody inside this substructure will have the same angles, etc. Or maybe it goes. This only describes up to the second deepest level, and it goes on and on like this. Okay, so yeah, then it becomes harder and harder to make pictures, but I'm still going to try a bit. So let's say with two lovers, we could imagine that so this is an equilateral triangle down there, and okay, I should not put the point. And then same here, and then same here. And so it's hard to really get convinced by what I'm going to say, but you should imagine that anytime I pick 2 points in this same small cluster, the vectors will have the same scalar products. Okay, maybe this is not so surprising. It's like the picture we discussed before. And moreover, each time you pick 2 points which are in different of the smallest clusters, these two will also have the same scalar product, a different value. Okay, so again, you can imagine that you do it like this second picture. You first pick a direction which is common to everyone. Then you spread orthogonally into 3 new orthogonal directions. And then from these new points, each of these, so now we have already 3 points in our tree. And then each of these points will have yet another threefold split, let's say, to be consistent with the picture, in which everybody goes to yet a new orthogonal direction. Okay, and this is now finally the construction that we will use. So yeah, so there's a question in the chat about why do I draw things on the sphere? Okay, so perhaps one easy way out of this question is to say, if you take the SK model, so somewhere in the assumptions I said the sigma square is equal to n, but that's not, so that's kind of an easy way to for me to move on. But in fact, it's not a very honest answer, because even if this assumption was not made, I would still want to think about it this way. And the reason is a bit more subtle. So I don't know if it's subtle, but the point is that here I'm trying to describe what happens generically for the gift measure that we care about. And I claim that, and so generically, I have to define precisely what this means, and this would take a bit of time. But at least let's go back for a second to the situation with query-based models and generalized query-based models. So here, generic would mean that if we move just a tiny bit the parameters, so generic means that things are true up to possibly moving a little bit the parameters. And so, for instance, for the query-based model, even the generalized query-based models, if you allow yourself to move the parameters just a tiny bit, then it's always the case that the sum of sigmas is concentrated. So if for some parameters, the sum of the sigmas will not be concentrated, but for some, it will be concentrated. And using a similar trick, I could concentrate the sum of sigma squares. Okay, so yeah, so I did not explain why the drawing is actually relevant. This is a non-trivial insight that comes from a lot of heuristics from the physics literature. I do think that that this guess like this with the Poisson-Dirichlet weights is reasonable, because already when we do these IID random variables, this is the picture we get. Okay, so the non-trivial new ingredient I'm putting here inside the picture is that, in fact, this picture can be composed multiple times. Okay, and this, you have to take my word for it a little bit. And this comes from, some insights that took a long time to actually fully clarify. But perhaps another way to answer the question is that I'm trying to describe what happens generically for these measures, as I was trying to explain waving my hands. And if you take an arbitrary Gibbs measure, a priori it could do all sorts of crazy things. And so even any statement of the form, oh, generically the measure will look like this, is a little bit crazy. And so let's say the more permissive my picture is, the less crazy the statement is. Okay, so it's more permissive to say, that it's this picture, or maybe a composition of multiple times this picture. It's less demanding to say, to allow for multiple compositions, than to insist that actually this is the correct picture. Does that make sense? Or, although the picture is more complicated, it's more permissive, right? And so it should be more plausible that to say generically the picture looks like this. All right. So indeed, now the goal is to, and so remember that, in this picture, the weights are given by this Poisson-Dirichlet process. And so here we will want that at each step, we build the object in a similar way, like using these Poisson point processes of polynomial tails. And then we normalize to get a probability measure. Okay, so this is what Poisson-Dirichlet cascades do for us. This is what we're going to define now. Okay, so heuristically, what I would like to do then is, so now let's forget about the geometry for a little while, and just try to make sure we're going to succeed in defining the weights with this associated tree structure. So what I would like to do is, so let's say we start from a root, and at first there is these weights of the Poisson point process, and then I allow that at each of these new nodes, we're going to attach a new point process. Okay, so let's say there will be UN, some Poisson point process with the intensity zeta1 over x zeta1 plus 1. and then there will be, so here the weight will be, so all of the, I'm going to multiply U1 by U11, U12, etc. So U1n, and then U2n, etc. will be independent Poisson point processes with a possibly different intensity. Okay, and they are independent also of the first layer. Okay, so if I want to know the value at this leaf, the one I put here, I multiply all the weights I find along the way, because there is U2 on top, and then there's U21. Okay, so here the weight is U2 times U21, etc. Okay, so now I'm going to, if this sounds blurry, I'm going to spend time defining this properly, and we're going to do this up to a fixed level, let's say K. All right, so let's fix, so I forgot what's the numbering of the sections, but now it's about Poisson-Dirichlet cascades. All right, so yeah, we fix some integer K. And I'm going to also choose these exponents, zeta 1 up to zeta K. Okay, so I said zeta 0 equals 0 and zeta K plus 1 equals 1. I'm not sure if I will actually use this, but okay, at least the relevant parameters are zeta 1 to zeta K. And yes, so now we go through these levels and we define these Poisson point processes. So for the root, okay, so let me, yeah, so how do we move around this tree? I kind of already used it implicitly, but so let's say the root, okay, the root is the root, and then the leaves of the root we will index by the set of integers. And then for each integer, let's say the integer 2 will have children, and these children will index by pairs of integers, 2, 1, 2, 2, 2, 3, 2, 4, etc. Okay. So in general, the tree so I'm going to denote n0. Okay, and n0 by definition is the set that contains the empty set. Okay, so this is the root. Of the tree. Okay, does it make sense? So we go along this tree. So if a node, let's say if so if I take an element in this set, so if it has length little k, then it is it is at depth k, and its parent is the element which is n1 up to n to the k minus 1. Okay, so I see that Luigi is pointing out that it has appeared already in Kavita's lectures. Oh, ça a peine. Okay, and yeah, so while I'm at this, so I'm going to define. So I want a notation for the parent at level L of this node, this node alpha. I'm going to write alpha, this vertical bar L. Okay, so for instance, alpha vertical bar k minus 1 is the immediate parent of alpha of alpha. Does that make sense? Okay, and now for each node except the leaves, we're going to give ourselves Poisson point processes. So for each, oops. That's right. So they are all independent of one another. So independent Poisson point processes of intensity. So it's going to be zeta k, no, zeta k plus 1 over x to the zeta k plus 1 dx. And we're going to denote it u alpha n. Okay, and it's n which varies from n to infinity, from 1 to infinity. Okay, so I have all of these Poisson point processes u alpha n. Okay, so in fact, you see that at each non-leaf vertex, I attach a Poisson point process, and I can imagine that each weight is attached to a child of this vertex. And indeed, as pointed out in the chat, on each level, the zeta k is the same. So this is so part of our claim would be that this is a valid picture. The things are splitting up, but they are splitting up all in the same way, in our branching. So the zeta k's will be of our choosing, like the H in the Curie-Weiss model, we were choosing some, we were just letting it be free. And similarly, the zetas will be free. Okay, so there are 3 parameters in the model, in the definition of the cascade. All right, so we have all these weights. And now the weight of, I want to define weights on the leaves, and the weight on the leaves will be obtained by taking the product of all the weights that we see along this path that connects the root to the leaf. So for each, I'm going to write specificity is a leaf. Oh no, I'm actually going to define the weight for every, yeah, okay, it doesn't matter. So let's say that for each vertex, even we define a weight, not only the leaves. I mostly care about the leaves, but set. It's mostly useful for proofs to have it defined also elsewhere, so that we can reason by induction. Okay, so I hope the picture is clear. So this corresponds to the thing I was trying to explain in this picture here. See, if I want to know the weight of this guy, so this guy is indexed by the pair 2, 1. What did I write? Okay, so let me go back. So I want to define a weight on this site. and we can call it, so the site is indexed, so is alpha equals 2, 1, and I want to define its weight as the product of these processes that we see along the way. And so I say it's U2 times U21. Okay. So U2 is the second value of the process which is attached to the root. And U21 is the first value of the process which is attached to the site indexed by 2. Sounds good. And so now I have these weights. And as I said, I mostly care about the weights defined on the leaves, and these W's. I mean, by attached, I just mean that they're indexed by these points. No. So okay, I see a question in the chat. So so far we have defined the U's, okay, and now I'm defining the W's as being the product of the U's along the path. Okay. So this formula is really what I mean. Like there's no typo in this formula. Does that make sense? And I think of this W on the leaves as being the behavior of the exponential of the energy function. Yes, indeed, I was wondering if this would confuse people more or not, but indeed, it's like a branching random walks, except when you do the summing, you should think it's happening inside the exponential, and so here we are already past the limit in some sense. So instead of saying, oh, we're summing inside the exponential, we're taking products of these things. Okay. Okay, so now, yeah, I think of this as being the behavior of the exponential of our energy function in the limit of large n, these W's. And now, if I want to have a model of a Gibbs measure instead of a model of this exponential, I have to make it be a probability measure. So what I'm going to do is look on the leaves, these W's normalize so that they sum to 1. Okay, so let's say, let me state a proposition first. So with probability 1, we have that the sum of these weights on the leaves is finite. Okay, so that's reassuring because I want to make this family W alpha become a probability measure. So at least the sum to something finite. So indeed, I can divide by this number. So I'm not going to give the proof, but it's in the handwritten notes, and it's by induction, and also using this. Last time we saw a property that allows us to integrate these Poisson point processes. When we have expectation of the log of the. No, yeah, this is not. Sorry, I'm making. We just also use the stability property. We saw that if a Poisson point process is multiplied by some independent random variables, then it still has the law of a Poisson point process. Okay, and you remember that we have seen that for like at least if k is 1, we have seen that that this is finite. Sorry. Okay, so this we have shown. This is the first level, and then you have to iterate this on and on. So yeah, I decided to skip the proof, but it's written completely in the handwritten notes, so you can have a look at it. All right. So okay. So in taking this statement for granted, we can define now these normalized weights, and this is what a Poisson-Dirichlet cascade is. Is these weights normalized so that they sum to 1? Definition. So maybe let me record the choices of parameters. So we have chosen an integer k, and okay, so and this zeta 1 up to zeta k, which are ordered and between 0 and 1. And from these, we have constructed this W alpha. Well, A in fact. And yeah, the Poisson-Dirichlet process, cascade, sorry. The Poisson-Dirichlet cascade associated with these parameters. So maybe I'm going to denote it as V alpha. So it's W alpha divided by the total sum. So this is the sum on the leaves. Okay, so it's a capital K. Okay, so capital K is the index for the leaves. Okay? So I should change notation. Beta here. Okay, so each V alpha is defined as W alpha divided by the total sum. And maybe the phrasing is not perfect, but what I really mean when I say V Poisson-Dirichlet cascade, I should say that the law, like this is, I fixed some parameters and then I describe to you a random variable. So really, what it describes is for each choice of these parameters, it describes the law of this random variable. And this is really how we should think about it. All right. Does the definition make sense? So maybe just one more time. So we have done this iterative construction of the Poisson point processes. We have multiplied them along the path of the tree. Just like for branching random walks, we would do sums, but except that we think that the sum is happening inside the exponential. And so in fact, we're taking product of these exponentials. And ultimately, we find some weights on the leaves, and we normalize these weights so that they sum to 1 on the leaves. Good. Okay, so now I'm going to add a remark, which I'm worried will be perhaps a little bit confusing, but I think it's important to notice that it's true. So here's a remark. So I'm not going to justify it, but just I think it's useful to have in mind. So one can show that the law of this vector as a point process, so the law of, so let's say V alpha in NK has the law of a Poisson-Dirichlet process of parameters zeta k. And in fact, it's not very difficult to show, like, because at the last layer, we are just having lots of independent processes with parameters zeta k, which are multiplied by some weights. And yeah, it's not difficult to show that for any frozen, whatever the coefficients are doing above, this will result in a Poisson in a Poisson-Dirichlet process with parameters zeta k. Okay, I'm not going to explain it, but I just want to point it out because really what matters when we construct the Poisson-Dirichlet cascade is not just purely the weights as a set, but is the weights as embedded in the tree that we use to construct it. Okay, so when I ask about, if I take two leaves in my tree, there will be non-trivial correlation between, let's say they are alpha and beta. There will be non-trivial correlation between V alpha and V beta, and this is something I want to remember. Like when I just think of these weights as just a collection of numbers in a set, this information about the structure of the tree is lost, and then the process becomes not interesting anymore. Okay. I mean, it's not that it's not interesting, but it's just back to the previous process we have already introduced. All right, so okay, so yeah, no, in fact, the proposition uses, so there's a question in the chat about why we assume, that's a very good question. I was wondering if I could manage, if I would just keep it under the rug or not. Yeah, the very good question is, why do we order these numbers? And so one kind of pragmatic reason is that otherwise this proposition is not valid. So when we apply this stability result using the previous layers, if you remember, the stability thing has some, we have this expectation of xn to the zeta that has to be finite, and so we have to make sure that from one layer to the next this works out okay, and so we need to have that these zetas are ordered in the right way in order to make it work. So that's kind of the pragmatic reason. Perhaps a more useful way to think about it is that we should think that this, in some sense, the multiplicity is of the configurations is increasing as we go down the tree. And if you go back to, so there was this toy model we discussed with the exponential of beta square root of n xi. So xi independent standard Gaussians and ordered from 1 to 2 to the n, and perhaps at least okay, and then we said the corresponding exponent zeta that shows up in the Poisson-Dirichlet process is square root of 2 log 2 divided by beta, as far as I recall. Okay. Modulo some small errors. And in fact, yeah, perhaps instead of thinking that this beta which is varying, perhaps it would be also interesting to see what happens if we, in this toy model, at least if we change the indexation. So if we decide we go up to Cn, and I'm not sure if I can explain it very well, but to me it seems plausible that as we go down this tree, we should think that in some sense we are increasing the number of things we're exploring. Like the C should kind of be capturing it. It should kind of represent something with a larger value of C. anyway, yeah, if we ask this question, the same question again, what does this set of values, their extremes, look like if we have exponential of Cn of them? And the answer is, I guess it's going to be square root of 2c over beta. And so indeed, as we kind of explore more of when there are more terms, we see a larger value of zeta, and perhaps this kind of makes some intuitive sense in some way. Not super clear, but yeah, it's like the basis of the tree is more common to everyone. So maybe there's less there are less terms, or there's less entropy, or yeah, that's the best I can do, I think. Anyway, maybe the best answer was that otherwise the process is not well defined. Maybe it's a good time for a short break, actually. So yeah, so let's take a short break, and as usual, I'm happy to take questions, and then we can resume in like 5-ish minutes or something like that. Yeah, so there's a question in the chat about this remark. Yeah, indeed. So let's try to imagine how we could prove it. Okay, so let me start by making a few remarks about Poisson point processes. So I mean Poisson point processes with this polynomial form, like zeta over x to the zeta plus 1. So if I take the points of my point process and I multiply every value by 2, by this mapping theorem, this corresponds to, is the same as saying that I look at the Poisson point process, which has intensity measure, the image under this mapping. And so up to some exponent of zeta, it will modify the, I will have to, I'm not sure if I will say it right, but I suppose that it will change the measure by 2 to the zeta, or maybe I'm mixing up the exponent, but something like that. And so then if we yes, so you see the Poisson point process, and of course if we normalize this to be a priority measure, we get the same thing because we have just multiplied all the values by 2, and then we take this out. Yes, that makes sense. Okay, and now so now let's imagine we have we're just taking the sum of 2 independent Poisson point processes. Then by this superposability that you're mentioning, the result is a Poisson point process with intensity the sum of the measures. So let's say they have the same measure. Then you get just again the same measure with a factor of 2, which by scaling, after you make them then if you rescale the weights so that they sum to 1, you will still get the same Poisson-Dirichlet process. Okay, so I'm not sure if I explained it very well, but then you can imagine that if you do this, it doesn't depend on the weights. In fact, like if you take your first Poisson point process, multiply by 3, then your second Poisson point process you multiply by 1/4, and then you take the union of these 2 things. The result will still be a Poisson point process with this polynomial tail thing, except with a constant in front. And when you normalize it to be a priority measure, well, you still get a Poisson-Dirichlet thing. And so whatever these things are doing above, then you're just multiplying these Poisson point processes by some numbers, and then you're looking at these weights as if they were just a big set, and so you will still get a Poisson-Dirichlet process. So the only thing that one has to worry about is to make sure that the thing is finite. Maybe this constant in front, you have to make sure it's not infinite. That's the only thing that one should worry about. And I think it's an interesting observation still, because so I'm not sure how best to capture this, but it says something which I would like to draw a parallel with infinite divisibility. Like I'm not sure if many people are well versed into properties of random variables that arise as scaling limits of sums of random variables, but all of these are infinitely divisible. And in some sense, so this Poisson-Dirichlet cascade is a much more complex object, but in some sense, it also has some sort of infinite divisibility, because like if you ignore some levels, what you see is still some Poisson-Dirichlet cascade. Like for example, if we build this, I'm not going to explain it well, right, but like there is something that if you ignore some levels and so some things are preserved, which okay, I'm not going to explain it well, so I'll stop. No, I guess what I mean is okay, maybe it will be clear a bit later. Okay, anyway, that maybe I'll stop here. So, I think what I'm saying is it's not very clear. All right, so let's resume with the discussion. So now I see on my notes that it's section 3. So I'm not sure if I got the numberings right, but let's say section 3 on the enriched free energy. So now we have the ingredients. So what I want to do now is build a random magnetic field, which has exactly the structure of the drawing I was doing at the beginning, with this sequential, each time we have a splitting, we have these Poisson point process weights, and then we go on and we have another splitting through orthogonal directions. We put some more Poisson point process weights, and we go on and on like this. And the only free parameter, so with the Poisson-Dirichlet cascade, we built an abstract tree and the corresponding weights. And now the remaining thing that needs to be fixed in order to build the random magnetic field is that we can choose the length of these little sticks that I was doing in the first drawing. So there was, I said, oh, you go some distance, then you go through orthogonal directions on the corresponding circle, and then you repeat on and on. Okay, so the lengths that you go by are free for you to choose. Okay, and this is the remaining parameter that we can play with. It's going to be denoted by Q. Okay, and I'm going to put all of these parameters, the Qs and the zetas, into one object, which will be this probability measure mu that we talked about earlier. All right, so let's do this. So now we are ready to define this enriched free energy. Let's write this. We are now ready to. And I'm going to do it for the SK model first. Okay, for the bipartite, it's not more complicated. It's just you have to do it on each of the two components, but it's the same way. So let's just do it for the SK model. So again, we give ourselves K, and then the zeta as above. And V alpha, the associated. So this is indexed by the leaves of this tree. The associated Poisson-Dirichlet cascade. And now I also take parameters to fix the lengths of these movements that I was describing. And so let's give them names. So okay, so again, for some reason I like to fix the endpoints, but I'm not sure if I would really need it. So anyway, so Q naught is going to be the length of the first stick, and then Q1, etc., up to QK. And they are not restricted, so. And we denote the measure mu is the sum for K from 0 to K of zeta K plus 1 minus zeta K delta QK. Okay, so in some sense, we see that this measure represents at least under some reference measure, it represents the law of the overlap between. Okay, so maybe I'm going to continue introducing definitions, and I hope that it will make sort of sense to encode this by a probability measure. So in order to pick these random directions, we are going to just say that we choose them at random all the time. And each time I do the drawings in my head or on the slides, I think of these as being picked on a sphere. In fact, I draw a circle because that's the best I can do in it's dimension 3, and then I want to say it's orthogonal, so then it's a circle, etc. But in fact, it's because we're in high dimension, it's just as well if I choose them to be Gaussians, because these Gaussians, they will live on the sphere, and they will all be orthogonal to one another anyway. So in fact, I will fix independent standard Gaussians on each of the which will be attached to the edges of the tree. Well, in fact, okay, I'm going to attach them to the nose, but so we also give ourselves Z alpha independent n-dimensional standard Gaussians So they are independent of everything else. Like, okay, everything else means our energy is Hn of sigma, so it's independent of Hn of sigma. And we set for every alpha on the leaves, we define this random magnetic field. I'm going to write ZQ of alpha to be sum for k from 0 to capital K. Ah, yeah, so I said Q1 is the length we add later, but in fact, Q1 is rather the sum of the two lengths. So let me write the formula. So I'm going to write 2qk minus 2qk minus 1 square root z of alpha restricted to k. Okay, so alpha is a leaf, and then I'm adding Gaussians with variance 2qk minus 2qk minus 1 at each level. Okay, so that I end up with in total, this is the Gaussian with variance 2q capital K. Okay, but you see that if I choose, let me write it. For every alpha, beta leaves on our tree, if I compute the scalar product between these two guys, z alpha and z beta. So imagine you're trying to do this scalar product. All of the Gaussians that we meet, they are independent. So the question is only when is it that the path that go to alpha and to beta are going to split? So maybe in the beginning they will see exactly the same random variable for a while, and then at some point the path split, and then they see independent things, and they are no longer correlated. Okay, so in this scalar product, all what will matter is the path that is common to alpha and beta. So what we will get here is 2n, n is because it's a dimension, times q of, I'm going to write like this, alpha wedge beta to denote the common ancestor of alpha and beta. So, okay, it's just the depth at which things separate. So where alpha wedge beta, by definition, is the soup over k of k such that alpha restricted to the kth level is equal to beta restricted to the kth level. Okay, and yes, so maybe you can say, but we're taking expectation, but also keep in mind that this is in very high dimension. So this is very concentrated near its expectation. So even if I don't take expectations, this calculation is essentially valid. These vectors are essentially as displayed in the formula. And so I claim that this is really realizing the picture that I was drawing at the beginning with the, we go some length, and then we split along this tree, and then we go on and on. Okay, and now at each of these leaf vertices, I'm going to, I want to make this correspond to a Poisson Dirichlet cascade weight V alpha. Okay. Oh yeah, and just also as a side comment, our initial guess with the kind of simple random magnetic field, you can recover by setting k equals 1 and just having just one parameter here. So it will be just instead q1 will be h. So let me write this in the margin. So our naive guess initial attempt, let's say initial, the one we did 2 sessions ago, is when mu is delta h, the Dirac at h. All right, so yeah, I hope you're still with me. So because now we are ready to actually define the enriched free energy. We have all the ingredients necessary for this. So let's do this. We define Fn of T and mu. So I like to put the minus in front, remember? And then this is the normal form. But now I'm also going to sum over the weights of the Poisson-Dirichlet cascade. So I'm adding a sum over alpha. So alpha in the leaves of exponential. So square root of 2t hn of sigma minus nt. That's our normal term. And now our magnetic field, zq of alpha dot sigma minus nqk. V alpha dpn sigma. Okay, so this is our free energy. And now I swear I'm not going to change it anymore. That was our initial guess. That was not good enough, but now this one is the right one. And this is still a random object. So we're also defining its expectation. Okay, does it make sense? So I don't understand the question. No, Q, I mean the vector of Q's. When I write ZQ, I mean, yeah, I mean the vector of Q's. The ZQ depends on all of the Q1, Q2 up to Qk. So it's just to keep track of the file, it depends on Q. And yeah, so you're in the, when we're doing our naive guess with just, it was just square root of 2h times the Gaussian dotted against sigma. What we're doing was sliding the h, okay, and differentiating with respect to h was convenient. Like we found nice derivative identities with this. It was not yet sufficient for us, but it was, let's say, the right move. And now I have this object depends on the zetas and also depends on the choice of the q's. So the q's are a generalization of this h. And the way I would like to think about it is that the zetas are very dense, but we are going to keep them fixed. So let's say maybe there are k is very large and zeta k plus 1 and zeta k is 1 over k. Is 1 over capital K, sorry. And on the other hand, we're going to move the q's around. Okay, so we're going to differentiate with respect to q. Okay, so first, the derivative with respect to t has not changed compared with what we have done last time. Okay, it's exactly the same calculation. We will get exactly the same thing as before. Okay, so now the bracket denotes the Gibbs measure with respect to our new energy function, like this big one. Okay. So the calculation is exactly identical. And now, hopefully, we have gained something when we look at the derivative with respect to the qk's. All right, so let's try to compute this. So I want to see what happens. So for each, let's say for k between 0 and k minus 1, and capital K minus 1. Yeah, I would like to maybe take some more space to compute the derivative of Fn bar with respect to Qk. So let me display one more time. The definition is here. And so we have to remember how the Qk appears in this guy. And it's displayed on top. It's this sum. So in fact, it appears twice. You know, it's as a 2qk minus 2qk minus 1, and as and in the 2qk plus 1 minus 2qk. Okay, so when we differentiate, what we will get is minus 1 over n expectation of 2qk minus, oh, sorry, 2qk minus 2qk minus 1, 1/2, or minus 1/2 z alpha k dot sigma minus, and then the other term, okay. And now we are again in a position to apply our Gaussian integration by parts. And we are trying to compute some expectation, and there is this Gaussian that is sitting here that is calling for being integrated by parts. Okay, so you remember how we proceed to do that is that we look at how, for each alpha and beta, let's say we look at the correlation between this and the Gaussian in the energy function. Okay, so there's this guy. How does it correlate with the energy which is here? And so, but for possibly different alpha. So the question is whether or not they use the same z alpha restricted to k. Okay. So the correlation will be, well, this term, if, let's say the 2 points are called alpha and beta, so it will be this guy if alpha restrict k is equal to beta restrict k, and it will be 0 otherwise. Okay, so maybe I'm going to write the result of this calculation. So in our formula for Gaussian integration by parts, remember it's like it was reading like C of sigma sigma minus C of sigma sigma prime. And here the C of sigma sigma that comes out from this term will be just the norm of sigma squared, and it will just compensate the one that will come from here. So I'm not going to write it. Okay, so the only thing that remains is the indicator function that alpha restricted to k is equal to alpha prime restricted to k. And then minus the same thing at level k plus 1. All this is against sigma dot sigma prime. Okay, so maybe I'm a little bit quick here, but what I'm doing is I'm looking at this. I'm going to say it again. So this, I'm thinking of this as a Gaussian random field indexed by alpha and sigma. And inside the energy function, this thing is also a Gaussian random field indexed by alpha and sigma. And I'm computing the correlation between any, this guy at alpha sigma and this guy at beta tau. And the Gaussian integration by parts tell me that the result of this calculation, let's call it C of all of these variables. What I have to write when I do the Gaussian integration by parts of this guy is C of the repeated variable minus C of the alpha sigma, alpha prime, sigma prime. Okay, and so that's how I get this term, and then from this term I get the other term. Okay, so I think it's good to that one sits down and verifies that this is true, but it's just applying the Gaussian integration by parts formula. Okay, and let me rewrite this a little bit. So yeah, when is this term not zero? So it's asking that if we want the first term to not be zero, it has to be that alpha and alpha prime coincide up to a level k. And if I want also this guy to be zero, I have to make sure that alpha and alpha prime do not coincide up to level k plus 1. So the two things happen simultaneously if and only if alpha and alpha prime coincide exactly up to level k. So I can rewrite this as 1 over n expectation of, so maybe I'm going to put the 1 over n inside. Sigma dot sigma prime over n, indicator function that the depth at which alpha and alpha prime agree for the last time is k. Okay. And so now, one last piece of information is that so also if you remember, we have identified the law of the overlap for a Poisson-Dirichlet process, and I claim that the exact same proof I have showed you allows you to show that. Oops. In this context as well, if you look at the probability that these two variables alpha and alpha prime, oops, oh, sorry, I'm confusing myself. This is 1 minus zeta k. Okay, so perhaps I'm realizing that there's one point I may have not explained carefully enough in the definition of the Gibbs measure. So let me pause and scroll back up and see if we all agree what is the definition of this Gibbs measure. Okay, so yes, so I mean, perhaps it's already clear for everyone, but just to make sure, now in our free energy, we are summing over this variable sigma as usual. We have this measure sigma. You can think of it as being a sum, and we're also summing over the alpha. Okay, so now when I write the Gibbs measure, I really think of it as being a Gibbs measure on the let's see, the random variables are sigma and also alpha. Alpha is also a valid random. Okay, so maybe to write it more explicitly, now I can, when I write an expression like this, I mean that it's integral sum of f of sigma alpha exponential of blah, 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 dp and sigma v alpha, okay, or maybe in the other way around. V alpha dp and sigma divided by integral sum exponential of blah, 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 V alpha dp and sigma. Okay, does that make sense? So that's what these alphas are doing in these expressions. Okay, and that's why also, once we have defined this, we can take independent copies, these replicas under this measure, and this I denote by sigma prime, alpha prime, etc. Yeah, I'm sorry that I was not, I jumped a bit too quickly on this point. Is this definition of the Gibbs measure clear now? And this is, yeah, so this is what is, when you see these expressions with the alpha inside here, for instance, you should always think that it's, if you want some shorthand notation for this fraction. Okay. And yeah, we can always apply this Gaussian integration by parts thing in this context, and that makes appear these replicas with the alpha prime. Okay, and now, yes. And now let me come back to this point here. So, I told you that these Poisson-Dirichlet cascades, if you, in some sense, if you look at them at some given level, you see at least at the last level, what you see is a Poisson-Dirichlet process with parameters zeta k. And I claim that, so now there are other things in the exponential, but the proof I showed you that gave this result for Poisson-Dirichlet processes remains, you can really just use it exactly identically without any modification to show that the display I showed is valid at least at the last level, for little k equals capital K. And I claim that if you're a bit careful, you can also verify that it's also true at the other levels. Okay, and so perhaps it's more convenient to rewrite this expression in terms of the probability of alpha wedge alpha prime being equal to k. And for this, I need to just subtract the same quantity, the same expression, but with k replaced by k plus 1, as we just discussed. So I claim that this is zeta k plus 1 minus zeta k. Okay, so a way to summarize the computation. Let me just. Let's say one way to rewrite this calculation ending here. I'm going to rewrite it as a conditional expectation. So I'm going to say zeta k plus 1 minus zeta k inverse times partial k of fn bar of t mu is equal to sigma dot sigma prime over n conditionally on alpha inf alpha prime equals k. Okay, and the conditional law is with respect to the joint measure. Okay, so I've done lots of things here. So do you agree that this is valid? So the conditional expectation is the expectation of sigma dot sigma prime over n indicator of blah, 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 divided by the probability that alpha wedge alpha prime is equal to k. And we just said that this probability is this. And indeed, I divided by this quantity on the left. So that is true. So far, so good. And yeah, now I want to explain why I think it makes sense to compute this quantity. And yeah, the point is that you should really think of Fn bar as being a function of the measure mu. In fact, yeah, if I had time, I would prove that it's Lipschitz continuous with respect to variation of the measure mu. So yeah, it makes sense to think about it this way. And now if you think that you have a measure which is a sum of Diracs, and you're moving the Dirac attached to, let's say, this case Dirac, which is at position qk, you move it a little bit, then the response to this should kind of be balanced according to the weight of the Dirac. So just to, this is only a little bit of a chit chat for why I kind of like to write the left-hand side in this form, like with a division by zeta k plus 1 minus zeta k. I remind you that, okay, so let me display one more time the definition of mu. You see this term in front is the weight of the Dirac at position qk. And I claim it makes sense to do this because in general, so this is just a philosophical digression if you want, but I mean, I could justify it more precisely, but if you imagine, for instance, that you look at, maybe I should not call it f because there are too many things to call it for it. If I look at the function of a measure, which is just the integral of f of x d mu of x, and I'm thinking that mu is the sum of Diracs, and I'm moving the Dirac at position qk, then what I will get if I do this, I'm going to get the partial of f at the position qk, but multiplied by the weight, zeta k plus 1 minus zeta k. Okay, so if I want to have some notion which is more consistent to really talking about the function g, like it would be nice that we say that the intrinsic derivative in some sense, it's kind of a transport type of derivative, which I could justify more precisely, should be the result of this calculation divided by the weight of the Dirac. Okay, so that in some, so maybe I would like to say that the derivative with respect to mu of g, which we will compute at a point, is partial x of f at x. I would like to say something like that. Okay, so maybe this thing on the left side has a notation. Let's say I could denote it partial mu Fn bar of t mu qk. Okay, so this is just a matter of notation, just to say that it makes sense. But what did we gain really? This is really the question. So we gained that now we can access the conditional expectation of sigma of this sigma overlap. So let me call this the sigma overlap, and let me call this alpha y alpha prime the alpha overlap. Okay, so what we see here is that now with these derivatives we can access the expectation of the sigma overlap conditionally on the alpha overlap. And so what we would need in order to say that we can close the equation is instead of needing that the sigma overlap is concentrated and it has small fluctuations, it will be enough if the conditional law of the sigma overlap given the alpha overlap is small. Okay, so that's what I'm going to explain tomorrow. And yeah, this is okay. So I'm going to come back to some of the things we discussed today, tomorrow, because I gave a lot of material today. So yeah, if you feel confused, tomorrow I will try to recap the important steps we have done today and then clarify why this is interesting. And then we will identify, we will see the relevant PD emerging, and yeah, we will not have time to prove that it's valid. In fact, I don't even know how to prove that it's valid, but at least I will give some indications for how to prove one bound. All right, so thanks a lot for your attention, and yeah, I'm very happy to take questions. Yes, so in fact, yes, there's already a question. So indeed, this right-hand side should depend on mu. It should also depend on t, right? Because everything is also a function of t. So these variables t and mu, they are both hidden in the bracket notation. So when I define the brackets, here is the definition on top. In fact, it depends on what is in the dot 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 in the exponential. And so in particular, it depends on t and it depends on mu. You need not that, sorry. You mean this? I suppose you mean this, yeah. Yeah, so in fact, here I look at a very simple function of the measure mu. It's linear in mu. So when I differentiate, the derivative in this sense no longer features a mu. But it's a special property of this specific function. So in general, when we compute this derivative, it will depend on mu. It's still a little bit to be clarified what this derivative with respect to mu means. But at least, okay, we should not feel too sorry if, yeah, when we take a linear function, okay, whatever that means, at least, yeah, okay, linear function. No, it makes sense. It's a linear function of mu, and yeah, when we differentiate, the derivative doesn't depend on mu anymore. And indeed, that's a big advantage actually of dividing by this zeta k plus 1 minus zeta k, because otherwise that would not be true, right? Because we would have these zeta k's around which depend on mu. So maybe that's another way to see that this definition has another good property. And maybe depending on the interest, I can explain a bit more. Or yeah, maybe I'll explain next week why this is a sensible definition. I mean next week, tomorrow. No, next week you'll be free.